I have to stop my share. And now, Jamil, are you on?
Hello, am I audible?
Yes. Okay, perfect. So, can you share your screen?
Yes, well, let me just take a moment to share.
Okay, while Jamil is sharing his screen. So basically, we tried to build a library that include all the different architectures to recommend teams. So from the FNN, BNN, and then also the training strategies, negative sampling, temporal training, and also there are some uh, there are some branches that are under development, for instance, the branches for end-to-end architecture. So it is not finalized, so that's why we didn't merge it to the main line. It's a branch. Also, there is another project, we call it Adila. In the Adila, what we do is thus receiving the prediction of a model, we try to re-rank it to make it more, bias-free or, fair. So we have two, again, OpenTF, so open source neural team recommendation or formation, and then there's another one, Adila. So Jamil is going to explain these two. We have another one, VivaFam, and also this. So Jamil gonna explain a little bit about how can you use it or how can you change it based on your need. Okay, Jamil, you can go ahead.
Okay, thank you. Hello, everyone. This is me, Muhammad Jamil Ahmed. I'm currently a master student at the University of Windsor. Currently, I'm pursuing a master's on computer science. And my research interest has been regarding this team recommendation. So, without any delay, today I'm going to be showing you some pre-compiled notebooks that we have at our disposal. So these notebooks are already provided in the website. So there are several parts here to discuss. So at first, we need to understand how we use the basic OpenTF that has been discussed by the base library that we got for our team recommendation pipeline. So OpenTF is the open source framework that is actually hosting the basic team neural team function process through kind of a conference pipeline. And there are multiple branches of it consisting of like fairness aware or time sensitive or graph neural network based methods. So today's outline will cover as I said, the basic OpenTF. Then we have for the fairness and diversified methods, we have Adila and VivaFem. And then for the temporal method, like the temporality aspects, we have temporal part of OpenTF. And then finally, we will focus mostly on OpenTF GNF. So I will take cover first 20 minutes or so regarding the fairness and temporality of OpenTF, and then I'll cover the graph neural network based parts. So here we have OpenTF have some basic arguments that we can just provide to quickly run a sample. So as we worked on our datasets, these were DDLP, IMDb, GitHub, and USPT on several versions of OpenTF. And all of these large-scale datasets have toy datasets at our disposal, and we have provided the toy datasets in our original GitHub repos, respectively, for the users to test. So you can see that we have some basic arguments like the data, the path of the data set, domain here, like which input domain the data belongs, like uh, that suppose the DVLP data that would belong to the domain DVLP, or the GitHub data that would belong to the domain as predefined as uh, Git, Git page. Then, etc. These are mentioned. These are detailed mentioned in the respective repository, GitHub repository. And then we have at our disposal models that we have on OpenTF. So in basic OpenTF, we started off with FNN and BNN as before neural network and Bayesian variational neural network. And then we channeled into several different directions that we will discuss later. Then here I'm going to demonstrate you with the Adela framework as a short run of the model. So for the Adela, we have several different arguments here, and I will explain them on my Adela notebook. But for now, we will just like cover the basic run, one basic run of the OpenTF. So let me just check if I'm at the right folder. So usually the root folder is OpenTF, and then in the source folder we have all we have the main.py that runs the actual pipeline. So in this case, suppose the OpenTF has the like as input it has uh, uh, it has a raw DVLP data. As we are running a small instance, we have a Troy DVLP data, and the domain is DVLP. The model is FNN and BNN. The fairness metric and some attribute regarding to the fairness. These are provided. These are some default metrics that have been the default values that have been given in the repository. So when we run this instance, it will show you that it will show you several different information here. Like what we do here is that run the model for threefold or fivefold cross validation. So in each of the folds, we have the number of epochs traversing for the training. So here you can see all the logs related to like as we start the model, we first load the team's vex.table file. That is actually the one-hot encoded embedding. Sorry, not the embedding, one-hot encoded input of skills that this team's vex has. So it is actually a one-hot matrix, and from that matrix, we pick the one-hot encoded skill sets. And then the relevant indexes of that one-hot encoded file, and then it runs, the basic training runs as an iteration of threefold or fivefold cross validation. And here you can see that in each of the folds, we have also like mini batching, sorry, excuse me. So in each instance, each epoch, we have the training loss calculating and the time covered. And then we have an early stopping feature that dictates how the model is going with the training. So these different settings, the fold, the number of epochs, the batch size, the early stopping settings, these can be controlled in a separate file called parents.py. So all of these are located in the source folder as we showed you. And after the training, you can see that early stopping trigger ready for 5. So whenever an early stopping is triggered, it means that the training is completed early and the model trained at the most optimized way possible. So then we do the evaluation, and we use the PyTrack eval library for that, and we feed them the required metrics that we need to calculate, like here, map cut, CT cut, precision recall, all at cutoff 2, 5, and 10 for our more exploratory ranking-based metric exploration. And then what it does that as Dr. Klein mentioned that the re-ranking for Adila is a post-processing technique. So what it does that after the training, as you can see, it applies the re-ranking or the fairness-based like approaches and tries to do the new set of evaluations. So this is basically a normal run the for a straightforward model like FNN or DNN. And there is a feature in OpenTF that we can run the training as a series of different training of the models. As you can see here, that we mentioned two different models in a model argument. So that means that it would follow a sequential pipeline, that it would train first the model on FNN, and then it would iterate another instance of training and train on another model DNN. So you can provide as many models as possible that has been given in the OpenTF library. So then we can check out the hyperparameters that we have at our disposal. As I said before, that there's a parent.py in every OpenTF variations we have. So this parent.py is usually located in the source folder, and you can see that you can almost you have a lot of freedom to modify the model running mechanism. So I will always show you the important parts that you can like look into, take a glance, and understand how much freedom you got. So here you can see that in the parent.py, we have a dictionary of all the parameters. So you can modify each part of the dictionary and mention the value that you desire for your own trading run. So, for example, for model, we can mention as which baselines to use. So in OpenTF, we have several different baselines as for now. So the basic ones are FNN and DNN. So inside those models, you can mention different more different granular settings. So here you can see that it's already described in the file with the comments that suppose L here means the list of the number of nodes in each layer. So if this is a list of all the layers that we need inside our P4 neural network model. So if it is 100, then that means that it is only one layer, 100 neurons. So if we mention 200 here, separating the 100, then we would mention that there are two middle layers, and it would be 100 neurons and 200 neurons. Then the learning rate, as you can see, these are self-explanatory. And then the batch size, the epochs, the number of negative samples, just as you might have seen, the negative sampling strategy, OpenTF, you can modify it and test on different settings. Then the negative sampling strategy, uniform, unigram, unigram B, or other available methods. Then the loss type here. So in this way, you can these are the very basic settings that you can modify. And other than that, you have a fair amount of settings that you can modify and include in the parent.py. So,
Jamil, just a sec. I just wanted to mention something. So, as I explained, so in order to have your own loss, so you can see that, I mean, in the pipeline, you already have different, I mean, curriculum-based losses or cross-entropy losses and etc. So one thing here is that you can just simply write your own loss function and you just inject it to the whole pipeline. So it's easily extendable to any loss that you want to define. This is one thing. Another thing is that, Jamil, can you go to the, the running parameter of the main.py? In front of the model. Yeah. So, yes, this one. It looks very simple, but it's very kind of, controversial, very challenging. The thing is that when you do a research, you want to compare your model with other models in a fair platform, meaning that on the same test set, all the other models, how they perform. So you cannot simply say that, okay, I just want run the pipeline for one test set and then rerun the entire pipeline from scratch for another model because the test is going to be changed. So here, this means that you can run the pipeline just for FNN, or you can rerun it for just DNN. But in that case, the training set and the test set is going to be different. If you want to just exactly see what happens with the same training set and the same test set for majority of, for a list of models, so this is what you can do. So before training the model for FNN and DNN, this split happens, and then the model sees the same set of training and same set of tests. So then the result gonna be way fair if you want to compare the results. Just that was just a quick note. Yeah, you can continue.
Thank you so much. Yeah.
And by the way, you have only about 40 minutes.
Okay, sure. So these are basically major settings. Then we can also, like as Dr. Pani said, we can change our pipeline to train, test about fair, and any other available methods to modify our pipeline and modify our experiments. That way, we have the freedom to do the comparison with whatever set of experiments we need to do. So then some more settings here. The data,
Sorry, John, I just wanted to jump again. I'm so sorry.
Yeah,
So
sure, sure.
these are, in practice, if you want to work with this library, you may face these issues. So one thing here, the command, the pipeline, you can see that we split it into phases. The train phase, test phase, eval phase, and etc. Why? Because when you wanted to train, for instance, 10 models on a single computer on a single server, so if you wanted to do the pipeline for all these steps, it takes a lot of time. What you can do is that you can simply, for instance, you can schedule 1 week just to train. So you can run the pipeline just for the training phase up until it produces the models and saves the models. And then you can run the pipeline just for testing on an available models. So because it works based on the lazy loading. So if the model is there, it doesn't train it again. So it loads it and then tests it. So it's not just doing the whole pipeline in one run. You can split it into different phases, and then for 1 week, just train the model. For another week, just test the models and etc. Because sometimes it takes time. Another thing is the filtering step. So in the data set, we'll see the outlier teams. For instance, just a single team with 5 experts that never collaborate again with each other. So how can you apply filtering in order to reduce the size of the data set, make it practical to training a model? So here are 2 filtering that you can do. Basically, we assume that in the data set, if you do this stat, you can see that there are many teams with one single author, and we do not consider them as a team. So you can simply put here mean team size 2. This means that only, pre-process the data for the teams that at least 2 experts are in the teams. And also mean team, number of team means that if there's an expert that has less than 5 number of teams, just remove that expert. So these are the pre-processing step to make the distribution of the data in the data set in a meaningful way. Yeah, go ahead.
Okay, thank you so much. So as Dr. Pani said, after running the model, the outputs are available. As I am showing you here, that in the OpenTF folder, after every training instance, as suppose in our example, we showed that the data was toy.dboc.json. So under this version of the dataset, we have all the selected outputs available after the training. So for the BFNN, we have all the settings that you set in the parents.py. It will get a folder of itself, and then under its own set of settings, it will have several outputs, as you can find here. So this is for example, sample file here that shows all the metric results. So in this way, you can actually gain an understanding how different models come into various performances. So I'll just skip this part right now as we concentrate on track timing. But these you can find on the GitHub repositories themselves, and they are explained well enough for you to start with. So here there are some you can extend the team class here, you can form a definition of the team yourself, consisting of different experts, and also in the OpenTF there are also definitions of like what should I say? Uh, Different hierarchies that you can extend for your own set of experiments. Suppose here you can see a hierarchy here that FNN, BNN extends from FNN, and then this FNN is extended from base NTF class. So in this way, you can find other different classes that you can extend and implement the desired methods that you need for an entire machine learning training pipeline. So these are the very basic features of OpenTF. You can find all the different code bases as mentioned in the different notebooks available to you. Now I'll just show you the glimpses of Dila, VivaFin, and Temporal that have more additional settings for their own set of pipeline. So as you have already explored about the fairness related training, so here for the DILA, we have additional set of arguments. As you can see, the attribute popularity, that when a model is biased towards popular experts, we can control, we can choose what attribute, we can choose the attribute to be the sensitive part for our model training. Then comes the fairness, that the metrics that we require for the re-ranking algorithms in ADILA, that is the vital part of the data. We can set that using the fairness argument. Then the NP ratio here is actually the ratio that you set for the non-popular experts to occur after the re-ranking. So there are other different arguments, but the major ones are, as I said, the attribute, fairness, and NP ratio. Then, as you can see, whenever we run a command using our specific set of arguments for DILA, the basic pipeline is still the same. As you can see, the model on FNN and BNN, we just train the entire model the same way, and then we apply the re-ranking accordingly, and then gather the results after evaluation. So this is basically the similar pipeline for DILA. Also, we can see this a similar pipeline for VivaFin.
Jamil, just one moment. So can you go to the Adila again?
Sure.
Yeah. One thing I have to explain is this. So sometimes when you want to make the result fair, it doesn't come for free. So you're gonna have a reduction on your efficacy. So you have to check the trade-off between the efficacy and the fairness. So in the Adila pipeline, we have some metrics. The OpenTF pipeline has the metrics for efficacy only. The Adila also has the fairness metrics, meaning that after you apply the re-ranking, you have to check the fairness. So it gives you a score. A high level definition. So it tells you that, for instance, it has NDKL, the lower the better, meaning that if the result in the final prediction has a lower NDKL, means that the result is more fair. But At the same time, the lower NDKL can come with a lower NDCG. NDCG is a metric for efficacy. So one thing this platform allows you is that comparing the efficacy metrics before applying the re-ranking and after applying the re-ranking, and see whether the fairness improves and also what happens to the efficacy metrics. And then you can select the criteria. For instance, if you go with the demographic parity and you put the ratio into 50%, 50%, meaning that you want to have 50% male, 50% female. So this, the re-ranking is gonna give you again 50%, 50% in the final. However, it may reduce the NDCG or other IR metrics way down. So you have to see what is the trade-off and what is the ratio for your domain. Yeah.
Okay, thank you. So let us look at the VPAPIM pipeline. So VPAPIM, as you know, that it's actually an in processing within the pipeline rather than the post processing in Zilla. So it also addresses fairness in a way that it tries to mitigate the gender bias. So the picture is self-explanatory that it penalizes the false negatives more and tries to randomly sample the female experts and reinforce their participation in the predicted teams. So for this, we already have a very similar pipeline, and for VivaPIM, we already experimented our approach, and the code base for the VivaPIM is still on the process of being incorporated into the main OpenTF pipeline. But the thing is that for VivaPIM, we have the very similar settings for the models, data, and the filtering, just the same way as Vila, with some additional arguments. And So in this way, we have both in-processing and post-processing fairness algorithms here incorporated into OpenTF. And then there is the temporal part of the information where we, unlike the traditional neural tree formation, we consider all of the teams in the same lane and space without considering the time as their differing factor. But in this new temporal tree formation, for each timestamp that we have, we consider the collection of teams within each timestamp as the strings of teams. And then we try to predict, given the set of the strings of teams in different previous timestamps, we try to predict the strings of teams given a set of skills, and we try to predict the experts. So we try to incorporate the temporality of different teams, which were not incorporated in the previous neural team formation pipeline. So what it does is we only have to incorporate the temporal part into the existing neural team architectures, which is into FNN and BNN, we incorporate TBNN or TFNN. These are the new classes that has been inherited from the previous classes and has been added with the temporal functionality. So evidently, the pipeline is still the same, and the training and all the different mechanisms occur in the same way as you can see, just like the previous instances that I showed. So here, this fairness and temporal part of the OpenTF is complete. Now I'm going to show you the graph neural network part, which is the main focus of our OpenTF pipeline right now. So previously, as you might have noticed, that we introduce the neural architectures with traditional one-hot encoded inputs of skills. So if we had to provide the model with a set of skills and we try to gather a set of experts as predictions, we would have introduced only one hot encoded skills, or a better approach was introducing them, inputting them with the embeddings of the skills themselves. So for embeddings, we had like in the team recommendation literature, we only had up to the last point, we only had some non-graph-based methods that actually improved our prediction of experts. But when we introduced the graph structure as input and extracted embeddings from this graph structure, and then input those embeddings in our FNN or BNN, then the improvement would be more noticeable. So this is where the GNN comes into picture. So previously, before GNN, we had MetaPath Select that was not a message passing based method. So now we have like utilizing the graph structure, we employ graph neural networks that can inevitably gather the best representation from a graph data. So in this view, we introduced like the graph neural networks to extract the embeddings of skills for the input of our neural architectures. So here the background comes as like if as you can see this graph structure, if we have a graph structure like this where we have a heterogeneous graph consisting of like different node types, like a team node, an expert node, skill node, and or location node, then we can represent the teams connected by consisting experts and their relevant skills. So each team would be interconnected to uh, each each of its experts and its relevant skills. So in this way, if we feed this graph structure into graph neural network, what it does is it employs a message passing mechanism, and by the message passing, it tries to do aggregation and combination of the neighboring nodes informations. So what do we have as informations? We have the initial set of features of the different nodes as our information. So in each iteration of the graph neural network, what the model does is it gathers uh, all the existing features or information, and then it does the necessary calculations to update the new set of features or information. So what happens is that after the entire training, the the skill nodes, not the skill nodes only, but the entire graph nodes get a new set of representations, which we consider as embeddings. And we only extract the skill part of those embeddings and take that for the further steps of neural architecture learning. So let's look at the graph structures here that we have employed in our OpenTF architecture. So here we have like three different graph structures. Um, so initially we started off with the STE graphs, right? That is the fundamental graph type we have at our hand. So we have the skill, the team, the expert, and they are only connected when they belong to the same team. So you can see that the skills of team one are connected to only team one. The skills of team two are connected to team two. The same way the experts are connected to their relevant teams. So if we remove the teams from this graph, we will get a skill expert graph. So basically, it will be the same graph without considering the team node. So the skill and experts will be connected to each other if they happen to be on the same team. And then we have advanced graph structure that has location node added. So what's the location? So whenever a team collaboration takes place and the location of the collaboration is found to be any location L, then we include that location as the node for that team. So evidently, they are interconnected if they happen to occur in the same team. So these are the three different graph types we have. So we abbreviated them as SE, STE, and STEL in our literature. And in the code base, following the hierarchy of previous OpenTF implementation, we had to maintain the translation of experts as members. So the only variation is the SE is translated into SM graph, STE translated into STM graph, and the STEL is as STML, like where the members are considered as experts. So then comes the neighborhood sampling. The very important part, how we can scale an entire graph into and fit into a GNN within constrained memory. So you can see this is a glimpse of a huge graph that we have in our hand. Suppose if you consider DDLP dataset as an entire data that has to be represented into a graph structure, then we must have a way to represent that data into a single graph, and then we should process subgraphs from that entire graph. So that makes us do the neighborhood sampling. So what happens is that at the starting, we have a graph at our hand, and we try to sample, we try to start off with a pair of nodes consisting of an edge, connecting an edge. So you should note that this task is a link prediction task that we make the GNN model train to learn the embeddings. So as it is a link prediction task, we sample the graph based on links, like based on edges connecting the nodes, not the nodes themselves. So if we start off with, suppose, a single link, then we could select a neighborhood consisting of all the immediate neighbors connecting one edge from a node to another node. So it would be a source node and destination node, and that would be a one-hop distance from that T1 node to the other nodes. So it would be a one-hop neighborhood that we can sample, and then similar way we can sample two-hop neighborhoods starting off from a node, and then like sampling edges starting off from that node, then sampling up to two-hop or k-hop edges that makes up the neighborhood. So what the neighborhood is, that neighborhood is the subgraph that we feed to our GNN model. So in this way we can.
Jamil, I just wanted to add one note. So one technical note actually is this. So can you go up a little bit for the graph structure? Yes, yeah. So basically the idea was that, what's the impact of graph structure? How, based on the graph that you form, how the embeddings or how the team recommendation can become better or worse. But what happens is that depending on the way you create the graph, it becomes sparse or dense. This has a huge impact on your running time. Why? Because if you just go with the SE, you're gonna have a very dense graph. So it's a bipartite graph, but it's hugely dense. You're gonna have millions of edges compared to the STE. So can you go scroll down a little bit? And then when you apply GNN method, so two parameters are very important: number of hops and negative sampling. So if you go with, for instance, a dense graph with 2 or 3 hops, it takes a lot of time. Why? Because everything is connected to each other. So it's gonna have, a neighbor of a single node gonna have many other nodes. So, and then it wants to aggregate information from them and then apply the combination function. So it takes a lot of time. So this is one thing. Also about the negative sampling. So if you have a dense graph, your negative edge is going to be huge. So again, this is another factor that you have to consider. So I'm saying that, based on the graph structure, you have to be careful about selecting the number of hops and the number of, percentage of the negative sample edge. When you are running GNN methods for team recommendation. Yeah. Okay.
Thank you so much. Yeah. That's why this neighborhood sampling technique is very crucial for the entire training that you have to do for the GNN part. Because by selecting or sampling a very good representative of the entire graph, you can improve the training overall. And if you have a bad subgraph that you sample from the entire graph, at each iteration, your model is going to learn the bad way. So there are multiple parameters for controlling those behaviors. We will see further. Now the entire architecture summarized here. So what happens is that we can either choose either any one graph structure, and then we feed it to the graph neural network model that uh, trains through the link prediction task, tries to predict any existing or non-existing link in the or edges in the graph, and by that it tries to learn the representation of the nodes themselves. And after the training, we you can see that we get the embeddings of each type of node. So we only select the embeddings from the skill set and then feed them instead of the one-hot encoded skills to the BNN or FNN. And finally, the pipeline is still the same after that, and we get our recommended expert. So the only difference the only difference from the previous approaches here in the pipeline is that this GNN part here. So whatever you have to modify, you have to do two-step. For now, you have to employ two-step learning. Like one learning step would be from the GNN that requires the GNN argument, and another step would be the traditional OpenTF pipeline. So let's take a look at that now. So um, here we have shown all the instructions to recreate the entire repository and to recreate the point from which you can start training the GNN models right away. So I would skip that part because that's the basic setup part. So like here, let's run. Let's first head. Yep. So yeah. So here, there are a couple of things to know here. Like the entire code base has like two distinct pipelines. So you should, as I showed you before, that under the source folder, you have the main.py. That was the main.py for OpenTF. And now, for the GNN part, right now we have under the source folder, sorry, under the source folder we have models for MDL, then team to vec, then means that for each team we convert the teams into, we vectorize the teams. So under that folder, we got several classes of GNNs and their relevant files, and that consists of the main.py. So this main.py here is the one to drive the GNN model. So for the, so whatever I explain now is for this main.py. So the embedding generation pipeline, we have emphasized on GNN methods, but for our research purpose, we had to incorporate all the previous baselines also for the embedding generation method. So we have MetaPath2Vec, Dr.Vec, and their relevant settings that you can find in the details. Then we have, as you have seen already, the graph attention networks, graph attention V2, heterogeneous attention network, graph isomorphism, then the GIN that is feature enhanced. So all the like state-of-the-art popular graph neural network methods we try to incorporate. Now we also have land at our disposal, and further we would like incorporate more different models. And one thing to mention is that the structure has been the structure of these classes have been made such that you can import any different any outside GNN model and modify it, like treat a very little bit of it, and you can incorporate in this pipeline. So given obviously given that it can handle like heterogeneous graphs, and also it can handle link prediction tests. So then this pipeline accepts like the input as team specs. This one is the like the one hot encoded vector matrix that the OpenTF pipeline provided to us. This was a very good utilization from the previous library that reduces our training time and like streamlines the process of pre-processing the input to graph-based data. So what we do is we take the team specs, one hot encoded matrix, and then convert it into our desired graph-based data. Then we select a model as either of the graph-based methods. Then to generate the GNN-based embeddings, we have to provide some arguments. So the major ones are like here you can see the aggregation method. So in the like for the GNN, when we form the graph data from the traditional T-specs data, there are occurrence of multiple edges between two same nodes. Like if there are two nodes that are like a source and a destination node, and between them we find multiple edges for several reasons. Then we can concatenate them or aggregate them based on different functions available to us. So that's the aggregation method used for the graph data. Then we have the embedding dimension. That's a very sensitive parameter. Like you have to understand your data and find the perfect dimension that suits your needs to result in a very efficient result. So that would be like after the graph neural network training, the size of skill-based embeddings will be according to this parameter. Then the training epochs, whatever epochs you need to train. So you have to notice that here each epoch means an entire iteration over the whole graph data. So if we do min matching on a big graph data, then after all of the mini batches have expired, have exhausted, so that would be one single iteration of one epoch. So then we have the pipeline that accepts the arguments just like the OpenTF pipeline. So this is the neural network part after the training of the GNN part. So you have the same set of arguments here, like the pre-processed, the data set version that we will use here. Also, the domain like TBOK, IDB, or GitHub, then the model FNN or DNN or any other model that has been provided with OpenTF. You can use any model here. I mean, the best part here is that you can use any model and they will accept any embedding output, the output meaning the skill-based embedding output from the previous method. So this is how the architecture has been developed. And then we have like for the GNN-based methods, like when we run the FNN or BNN, we have to mention that the input will be from the GNN-based method embeddings. So in this way, if we mention these two optional arguments, we will run the same pipeline like OpenTF, but it will understand that now the input will not be the one hot encoded skills, rather the embedded skills from the GNN models. So as you can see here, embedding graph type here, SM or STM that I said translates into SE or STE type graph. In this way, we can run a sample pipeline of the OpenTF with GNN. So here you can see we have got the GNN part here. Like this is, you can notice that we are in the source MDNO Team2Vec folder. Inside that, we will call the main.py. And by calling the main.py, we can pass in the graph neural network-based arguments. And you can see that we are passing the toy DWB data. Then the model here, we have to mention as gnn.get or gnn.gs, gnn.gin. These are like self-explanatory based on the model you need to pass on. Sorry. Then the aggregation method, as I mentioned before, the aggregation of the graph type, then the number of epochs, then the dimension as 8, then the negative sampling, as Dr. Fanning mentioned, the negative sampling of the edges. So if you negative sample 5 would mean that for every single positive or existing edge, there will be 5 more negative or non-existing edges that will be created. So they'll be labeled as 1 for the existing edge and 0 for the non-existing or newly generated negative edge. Then the graph type, that's already mentioned, STM, skill team expert, or skill team member. So then, when we run this,
just a quick note that we have only 1 minute.
Okay.
So if you could just show the important part, that would be perfect.
Okay. So when we run this command, then you can see that we have the information of the entire model architecture, and then the training happens, and we are calculating the validation AUC validation losses, and based on the validation AUC, we can employ early stopping also. So after the training, figure saved, and after any evaluation, the embedding is saved for the next part. And we can, the same way that we did for the OpenTF, we can feed the embedding instead of the one hot encoded skills. like mentioning the embedding model as GAN and embedding graph type as TEM, and mentioning the other relevant optional arguments that we already mentioned for the graph-based part. And the rest of the part will, will be exactly the same as we showed for OpenTF. So this is how we train the entire graph neural network based method in two different pipelines, one for graph neural network based pipeline and another one for the basic OpenTF. So this is all for today's session. I hope you enjoyed the entire part. Thank you.
Okay, thank you so much, Jamil. Thank you so much. So we are, I mean, we have just one more or two more. Yeah. Before that, I just wanted to show you the. So if you stop your screen, Jamil, that would be perfect. So then I can.
Sure, sure. Okay.
Okay, perfect. So I just wanted to show you the actual pipeline which is missed. So if you go to GitHub, Funny Lab, so this is the OpenTF. As I said, there are many branches, so each branch is based on the accepted paper in each conference. But right now, the GNN branch is based on the idea of end-to-end approach or transfer learning for GNN. We have the VFM here. Also, we have the, curriculum-based learning here. So these are different branches. The main is not updated with those branches that are underdeveloped. For instance, the VFM is not merged with the main, so it's underdeveloped. The GN is not merged with the main, so you have to run it, as Jamil said, separately. So basically, I mean, whenever you are cloning the code line, be careful which branch you're working. And again, we try to add as much documentation as possible. And this is one thing. Another thing is your feedback. So can you please scan this barcode and let us know how can we improve this tutorial? Which part was not good? Which actually all parts were good. No, I'm kidding. So which part actually needs improvement? Which part needs more focus? And should we add more technical part? Should we add more philosophical part? Problem definition part? So this way we can tune our presentation for next series of conferences. Yeah. Any questions?
Yeah. So I have a question. Could you show the comparison between the end-to-end approach and transfer learning 177?
Sure. So
I think this setting is totally setting with the problem itself. So this end-to-end, we show 177. In the previous one, just try, anyone can join any new task. But this task is just an author prediction task. Providing the paper as a set of keywords and try to identify those.
sorry, I didn't get the question, sir.
Yeah, this one, since topic is maybe related to the paper, team corresponding to the paper.
Okay, so for instance here, this is the one paper.
Yeah.
And these are the keywords attached to that paper.
Yeah. In such a case, it's an author prediction task based on the set of keywords.
Yes, yeah. Author, yes. Yeah.
It's not a team formation.
So that's the thing. So it depends on how you look at the problem. So basically, if I include that, what's the probability of all the authors connected to that team? It becomes kind of similar to this part, but again, these are the predictions on the links. You're right. Again, you are predicting authors, but based on the link of that author with that specific team. In terms of computation, still we have to calculate all these probabilities.
Yeah, and if those kind of embeddings, including the community-related issues, that improves the performance much better than the first.
Exactly. Yes. True. Yes.
So
But one thing is that in this architecture you can augment more edges that are not in the actual graph. For instance, if you simply say that I'm trying to. Yeah. For instance, you can say that if two authors, like collaborative filtering in recommender systems, if two authors already work on the same project, not on the same, on different projects that share the same skills, you create a link between them. For instance, if these two authors, this is from company A, this is from company B, but they are in two different papers, these two different papers are sharing the same keyword. So then, based on collaborative filtering, if you can connect an edge between these two experts, you are letting the GNN to aggregate the embeddings based on these paths.
Yeah, but on the contrary, there are a group of people who would like to cover similar kind of aspects. That is a laboratory. Those kind of keywords are common for those kinds of papers. That will characterize the community, and that will characterize the paper. That will characterize the author.
True. So no, I'm saying that okay.
I didn't criticize your method, but please be careful. What you are doing is what you have tried to solve. Please try to clarify.
In terms of, I mean, so you say that are we going to find the communities, or are we doing the team recommendation?
Yeah.
That's your question.
Yeah.
You are right. But one thing is that in the literature, some researchers look at team recommendation as community prediction. This is one thing.
Yeah.
I mean, they look at this like that. But you're again right, because the task should be different, because I mean, usually community detection is a modular structure in the graph, and this way we are also going to that direction. But what I cannot see is that what's the problem? I mean, if we look at the team recommendation, I'm not saying that it's a problem.
Yeah.
I'm saying that we have to make it clear that, I mean, there is a link between the community prediction or community identification or community detection and team recommendation.
Yeah, I think
So
that is the most important aspect. Your performance is significantly better.
Gotcha. Yes, true.
So
true.
you cannot say this is good for team formation in general. This is good if you consider the community identification. Yeah, that will be a good sign. I didn't say anything about you but please try to clearly separate what is the issue solved by this method, and what is the issue tried to solve in the previous method, and so on. So all of the things is a mixture. That is the one thing I have a comment for this.
Gotcha. I see now. You're right. You have to make it more clear that, for instance, if you include some slides about community detection, and then we, in this presentation, we try to make a distinction between group and team. But if we could have some slide in order to explain that what is community, is there any similarity with community and team recommendation, and what are the distinctions, then it makes it more clear. Oh, you're right, yes. Yeah.
Thank you for the nice tutorial.
No, thank you. Thank you, but that was a nice comment. Thank you.
Give me just 2 seconds. So you mentioned, I think around slide 215, roughly. It was about the using the group learning. So you were saying that the groups, like when they're not formed systematically, I think it was just maybe 1 or 2 slides before this one. It was saying that, like, so when the groups aren't formed systematically, like generally like student groups, then we have generally a lot of issues. But so the data sets that we are using for these supervised machine learning problems, are they also data sets that are generally groups that are not systematically formed? And if that is true, since we're kind of using these data sets that have these, I guess, inherent issues, can you talk a little bit about how that can kind of create maybe a little bit of a loop of, where we're trying to predict something based on a data set that we know has all these issues? As you say, these models aren't quite strong enough to be performed, to actually be deployed yet. So generally, yeah, I think you got my question.
That's a very good question for Matthias. Yes, that's a very good question. So what do you mean by systematically?
The previous work on group learning mostly, rely on social science and not go to, not formulation, not based on the formulation, and also, I can say that based on the specific attributes, we don't have any work that, mostly focused on different attributes which are important in this domain, only based on some initial, properties, based on, especially based on some, methods from social science about the, we have some methods, I dropped it from my slides because of the timing. We have some, methods in social science try to group the people based on some characteristics. So it is mostly rely on social science related objects. That's why we can say that, by systematically, we mean specific formula, specific attribute, which consistently used by different work. We do not have anything, in this domain. And, the thing that we suggest is that different attributes can be added, in a uniform structure to the network, and by a unified, network, then it would be possible to, to look at the problem with, a specific method and formula. It was the thing that, it is the thing that we wanted to suggest this as a potential, problem.
I just want to add another thing. So we already started a kind of, applying for a grant for education, and we found that although these instructors try to ask the students to form group, no documented artifact actually exists. For instance, we don't know in the previous semester what was the group, the outcome of groups. So one way we can look at it is that there is no data set right now in education, and because in education the student privacy matters and etc., nobody has started creating a data set that shows the result of student teams or student groups in one semester, next semester, and etc., or during the whole, undergrad studies or grad studies. So this is one thing that we wanted to apply. We want to apply for a grant to start collecting. This is part of the systematic approach to group learning. Yeah.
Sorry, one other thing that I add. For example, some work try to consider, to form the things based on availability. The other work based on the average grade, and they improve some methods, but without any comparison between the works. So we can say that it is not a systematic method, because we need to compare, we need to add something to the previous, works, and in this way, it would be possible to, to improve the method. But in the existing works are completely separated. Based on one assumption, try to do one thing without any comparing with other works, and it is a start.
That makes sense. Thank you so much.
Just a quick question. In various research topics, now researchers are trying to leverage large language models to solve their problems. So do you think there are any possibilities to use LLMs for improving the team recommendation?
Actually, yes, but I'm looking at this application in a totally different way. So it kind of might be very, imaginary, but right now we know that we can fine-tune language models for different tasks. So we call it agentic, tasks. So the next idea is that all these methods is trying to recommend the actual people or person. But what if we want to apply these on language models? So assuming, because here, if you want to form a team, you apply this model, and there are some privacy issues. You have to consider the fairness. You have to consider everything. Yeah. So, but assuming that I have a pool of language models, each of them are expert in one or two skills. For instance, one language model can be expert in answering the coding questions, another one, etc. So you have a pool, for example, 100 pool of different language models, and then you want to do a specific task. So you just simply look at the team recommendation model and ask that the team recommendation model to recommend language models to do the task in collaboration. And that's one interesting, so we call it agentic team recommendation. And I have this in my mind for next 2 years to start working on that. And I know that right now, I attended a seminar, I think it was in CIR 24. They created a platform that you just pick your language models and then you try to fine tune it for a specific task. So basically you can, right now, you can create a pool of language models, each are expert in different fields. So the next step is that based on availability of the language models, based on the price of the API calls, etc., how can you form an optimum team of language models to do your task? That's also an interesting. This is one thing, but in terms of the actually using a language model to recommend a model, right now I've not done anything. Once I tried to see, but I believe that it's not the main working stream of language models to recommend people. So even if right now you ask the language models to give you some team members, they are highly biased toward the popular scholars or people in that domain. So they do not consider, for instance, an undergraduate students or a graduate students who is not popular, but who can do the actual coding. But they are just recommending the profs. So, a team of profs who cannot do anything, yeah. So, that's one thing that, I know, but, yeah.
Yeah, because I imagine, to use language model to generate recommendation reasons or something, explore recommendation. But so, yeah, it's interesting to regard language model as a team member.
Just kind of related answer to your question, language models are just transformers, yeah? So seq-to-seq models that, whether they have recurrence or not. So we have a branch NMT, Neural Machine Translation. So because you know that the OpenNMT, the library that includes all the transformer models and seq-to-seq models, we tried to reformulate the team recommendation as a seq-to-seq problem, meaning that the input is just the sentences of the skills, the output is just the sentences of the experts. So if you use this branch, you can basically just a wrapper over the OpenNMT. It tries to apply all the different transformers or different seq-to-seq models for this specific task. The result is not that good. So, and there are some reasons for that. For instance, in the seq-to-seq model, you consider sequence, but in team recommendation, there is no specific sequence. So you have a set of skills. You don't have a scheme of skills. So maybe that's the reason for low performance. But again, I mean, this is kind of related to fine tuning a language model for this specific task. Yeah. No problem. Any other questions? So, one more time, I just wanted to go to the last slide. I really need your feedback because sometimes I think some part is very important, but it's not interesting for the audience sometimes. So I have to, so thank you so much for your attendance. Hopefully it was helpful, and we look at your feedback and we try to improve it. Thank you so much.
Thank you. So, sometimes data qualitative study shift biased by the characteristic.
Exactly.
I understand your stuff. But if you're focusing on how to improve the score for recommendation. Even like some students or some groups of members.
I said it's in,
Sometimes
it's not in,
include, that will be, I understand. Like half hour of data. Your main motivation can be evaluated. Somehow, we should be careful.
Not to confuse. I understand that. Sometimes in your research you think that you are showing something, but no, you are not showing that. This is interesting for me because in my PhD I did chemical architecture. And now that I'm looking at that, basically you are showing the efficacy of team recommendation, but based on the community.
That kind of bias can be included. And even final method utilize that kind of information more. That's a reason why such.
High performance.
Yeah.
Well, one thing is, because it is the graph, but for the transfer learning, at the end it goes to the forward classification, so it doesn't see the graph. So that's why it is a drop there.
Another interesting thing is that, based on the fairness group, it's very nice to have a such a kind of professional framework to discuss that kind of thing. For example, basically, if you just focus on some simple part, the recommendation like minor, some group with minor experts, for example, Python, or something, something a good method for recommending one team. But if you do it for a long time, there are several groups who have minor, more work based on such kind of recommendation.
After some time.
Actually,
yes.
I received this feedback. Yes.
So this is a real.
So you said you're going back to your postdoc people.
I'm not sure, I just want to ask that.
Community of social group. Japanese government. There are varieties.
That's so cool.
Because of that lack of persons who have such kind of expertise, those kinds of should belong to varieties of committees work too hard for representing group.
So that's the thing. So in one of the subgraph optimization, there is a constant called load or the number of tasks an expert can take.
Yeah.
And in the capacity. So in subgraph optimization or in OR, they put a limit. They said that okay, if that person is assigned this task, it is out of pool. However, again, that's why we wanted to do this. In the neural architecture, we have to think. Yeah, we have to think about how the model, when it gives a high probability for the, the current skill set, for the next round, it doesn't consider that expert. So it becomes out of the pool, or it reduces, the chance of selecting that thing. But yes,
I think that kind of things that where computer scientists can contribute to the such a kind of social skill design.
Yes.
Yeah,
so that's why, so far, whatever study, usually the psychology or the industrial engineering, they talk about information, etc. But at the end of the day, it's just a policy that should be done by a manual person, manually by a person. There is no connection between, the computational models, and then at least the model gives a recommendation, then there is a manual process of that.
Yeah.
That's, just 2020 or 2021, the computational model, fast computational model for team recommendation happens. So hopefully in the next 2 or 5 years, if the results are kind of reliable, and if the big companies like LinkedIn or those companies that gives talent search or job search, if they invest on this, then the community can see the effect, and then gradually, the society relies on this type of recommendation.
Yeah, social scientists may evaluate 4 or 5 years ago, but really happened. But even the computer scientists can do such a simulation and pointing out some problems much more earlier. So yeah, I think you have such kind of method, and some government policy may can encode it in that way and do some simulation. What happens? Maybe that will be
in the next 5 years, what happens to that society based on the recommendation of this model?
I hope you have a
Thank you for your comments.
Thank you very much. No. Oh, we already have the recording, so I was about to get a note of your comments.
I also you also enjoy the stay in Japan.
Yeah, this is my first time in Japan, and the thing is, when I was a kid, in Iran, they usually play the animations or cartoons from Japan. I think the most famous one is just the animation about soccer, Tsubasa.
Tsubasa, yeah, Captain Tsubasa.
Exactly. And then it was kind of dream or
exactly.
that we can actually see. And also I'm an avid reader of the Murakami's books. Right now I want to go to the library. When I imagine those characters, because he describes the characters very meticulously. So when I was imagining those characters, now that I'm walking in the streets, I can see them. And that was very interesting.
Yeah. I hope you enjoy the stay.
Thank you so much. Thank you for it.